Good day. This is Geo Lesson 2.1, which means it's the first lesson of Unit 2. And we're going to jump over to my DocuCam. So I'm going to share the screen to begin. So let me adjust the camera a little bit here. Okay, so as I said, this is lesson 2.1, and it's covering congruent and perpendicular line segments. And so what will you be able to do? You'll be able to identify and construct congruent line segments and perpendicular line segments. This video is going to support the IXL geometry lessons B7, B8, and B13. You're going to take notes on this as we've been doing in Unit 1 in your math notebook. And you will also explain how you can use what you learned to solve a problem that you think is similar. And then when you are done with taking your notes, and you've finished the video, you must upload your notes to me. And you may use the student view Dropbox. It must be turned in by 11:59 p.m. And I've extended the time for this particular video and the next one we're going to be doing 2.2 to 11:59 p.m. Wednesday of next week. So this week that's coming up. That gives you a little bit extra time, and it allows for the fact that these videos did not get out quite as early as I expected them to. All right, the first thing we're going to do is we're going to look at an example, and the example is represented by these two geometric figures here. One appears to be a rectangle of some kind, and or a parallelogram possibly. We don't know for sure. It's a four-sided figure. And the other one is a line segment. And it says are CD and EF congruent? So you have to find CD, which is here, and you have to find EF, which is over here, and you have to determine whether or not they're congruent. So two line segments are congruent if and only if they have the same length, even if they are part of two different geometric figures. And that should be if and only if. And it should be they have the same length, even if they're part of two different geometric figures. That's the biggest thing. These are two different geometric figures. And so it's okay to state the line segment that's in the first geometric figure over here on the left is congruent to the line segment that's represented by what's in between the points E and F here, so long as you can determine that they are indeed congruent. So the measure of CD, if you look at CD, is 171 kilometers, and the measure of EF is also 171 kilometers. So the two of them are congruent. And now what I've shown here is a congruent sign. So this is a geometric notation symbol. And what it means is equal in all ways. So that means their measurements are equal, their shape is equal, their size is equal, because you're looking at two-dimensional figures, and so also sometimes figures rendered in 3D format. And so you want to be able to say the same in all respects. That's what congruent means. It's a little more than equal. Equal's really limited to algebra. Okay, so let's look at our next example then. What is the measure of TU? So in this next example, we're looking at this figure here. And so it looks to be, kind of looks like a bow and arrow if you look at it, you know, very romantically. This from U to S being the bow, TV here being the arrow, and then the drawstrings being TU and TS, the drawstring being pulled out. So, but you know, we can also represent this as a triangle with a bisector through it, which happens to be perpendicular, we know, to the line down here, which is line segment US or SU, depending upon which way we look at it. So the rule is a point is equidistant from other points if it is the same distance from them. So if you look at the point V here, you'll notice that it is equidistant from U and it's equidistant from S because the distances are the same. They're 37 units for both. So the perpendicular bisector theorem, which is the rule that we're going to be using for this, is based on this concept where we have a bisector and we have a 90-degree angle. Perpendicular means that the two lines are at a 90-degree angle with each other. So that theorem states that a point is on the perpendicular bisector of a segment. So on the perpendicular bisector, in this case, that's this TV. This is the bisector and it's perpendicular. So it's this line we're talking about. So a point is on the perpendicular bisector of the segment if and only if it is equidistant from the endpoints of the segment. So V is on the perpendicular bisector, and it can only be on the perpendicular bisector if, again, the points on each side are equidistant from that point. And we see that here. But if you go up the bisector to T here, T is also on the perpendicular bisector. So is it equidistant from the points on the segment? We'll look at U and look at S. The question is that the case? Well, we don't know. We know that TS here is 51 units. What is TU, which is what they're trying to determine here. Okay? But if I'm following this theorem, it would stand to reason that since V is on the perpendicular bisector, and therefore the endpoints of the segment that goes through the points that the point V is on the bisector, but it is also on this line segment US or SU, and the rule is that this is only a perpendicular bisector if indeed the endpoints for U and S are equidistant from V. Well, the same thing has to apply up here. T has to be equidistant from U and S as well. So that's just in a nutshell what's going on here. If TU is 51 units, then UT has to be 51 units. So we'll see it proven out here. So if you look at the figure, I've enlarged it. They go on to say, okay, since angle TVU is a right angle, well, all right, where's TVU? TVU, it's this right angle right here that's being talked about. And SV, that's this, equals UV, and UV equals 37, then TV is the perpendicular bisector of SU. So they're telling you these two are SV and UV are the same measure, and UV is 37, so both of them are 37, okay? And it's already shown to us here. Therefore, ST is congruent to TU by the perpendicular bisector theorem simply because it also is on, T is also on the perpendicular bisector as stated. So in this case, TU equals ST, and ST equals 51, therefore TU has to equal 51. So there's your answer. Okay? So take a look at this, and again, think about this like a bow and arrow. TV is your arrow. SU is your bow. You pull the arrow back. This is the string that goes from U to T to S. And if you pull it back, you have to pull it back straight. So the arrow is going to be equidistant from the ends of the bow, and the T up here where the arrow and the string touch are also going to be equidistant from U and S. So V is equidistant from U and S, T is equidistant from U and S. And so since ST is 51 degrees, UT has to be 51 degrees. Notice that even though UV and SV are both 37 units, that doesn't mean that ST and UT are both 37 units. When you draw the string out, it stretches and things get longer. So you've got 51 units for one side. It just the other side, UT, has to also be 51 units. So these two sides have to be congruent. These two sides have to be congruent. But these measures are not the same as these measures here. Okay, that's the only other thing I wanted to point out for that. So let's move on. All right, so now we're going to go to constructing the midpoint or perpendicular bisector of a segment. And so you see this really weird, kind of complicated looking drawing, and they want you to mark the midpoint of AB. Well, AB is this line segment, this right here. Wow. Okay, well, why the circles? What's going on? Why the line? So we're going to go through this because what we're going to do is we want to construct the midpoint of a perpendicular bisector. So we have to establish that we have a perpendicular bisector going here. So we have to start somewhere. And here's what we're going to do. We're going to again use the perpendicular bisector theorem, which again states that a point is on the perpendicular bisector of a segment if and only if it is equidistant from the endpoints of the segment. So Z is equidistant from the endpoints W and Y here. How do we know this? Because you see the two tick marks, that means congruency as well. You don't have to put numbers in there, you can use the tick marks. And they're single tick marks, so they mean one is congruent to the other. Likewise, X here. It's on the bisector, and it's perpendicular, and it can only be on the perpendicular bisector only if its endpoints W and Y are equidistant from X. And you'll see there are two tick marks on each of these two sides, so that means they're congruent. So we want to create something like that. And so we've got to do something called a construction, and we're using now tools that the ancient Greeks used to use. They used physical tools. We're going to use virtual tools. We're going to use computer tools. So I'm going to be jumping back and forth between Desmos's construction tools. So Desmos is an app. It's online, www.desmos.com. I've given it to you. You've got that now in your Clever page and also on the Unit 2 lesson links page. So we're going to start by drawing line segment AB. All right, so I'm actually going to go over to Desmos, and I'm going to draw line segment AB. So I'm going to stop the share moment, and I'm going to go and share again, and I'm going to go over to, looks like I have to do one other thing. Let's see, share the screen. Not sure if this is what I want. Double check. Yes, I want my Desmos screen. Here it is. So here's the Desmos screen. I'm going to stop the share and start it again. There we go. There it is. Okay, so I'm going to draw a line segment. Now, to do this in Desmos, what you do is you go over here to the left to these tools. And in this case, let's just look at this. You can select a point, a circle, some kind of polygon, which is a straight-sided figure. So each of these sides are straight. They're formed of line segments, or an angle. And you can also do a line segment, a line, array, something called a vector, which we aren't going to use right now, and an arc. Eventually, we're going to get to using all these tools. And what we're going to do is we're going to go over here to a line segment, and we're going to draw one. So it highlights a point. I'm going to click the point, and then I'm going to draw a line, and now I've got a line segment. And I don't have the ability, again, to put in letters, so I can't put in AB, but let's just say that this is line segment AB with A being at the top. All right, so then the next thing I'm going to do, let me go back, stop the share moment, and go back to my DocuCam. And now I've created this line segment on Desmos. So what I'm going to do next is I'm going to draw a circle with a radius of that line segment AB. Okay, so I'm going to do that on Desmos. So I'm going to stop the share, and I'm going to go back and share my screen one more time. And I'm going to go over here to Desmos. And so here's a circle. And we're going to call this upper point A. So I'm going to click that, and then I'm going to expand the circle all the way over so that the point B here is on the outer edge of the circle. So now I have the circle that I showed, and I've got this line segment AB. So I'll call this circle A because its center is point A. All right. So let's go back and let's look at the DocuCam again. And so we're going to draw now a circle with a radius AB centered at B. So we're going to draw a second circle. But what we're going to do is, instead of drawing a circle around A like we did up here, here's A again, we're going to go over here to B, and we're going to make it the center of a new circle. And it's going to have the same radius. It's going to have the radius AB here. Okay, the same radius. All right, so let me show you how you do it. So you go over here to your DocuCam again. Let me share that. Oops, not that. There's share screen. And go to Desmos. And so now I'm going to use point B, which is on the perimeter, as my center. And I'm going to first click circle, click the point, and then I'm going to expand out again until the outer edge of the circle that's centered at point B goes through the point A. So now I've got these two interlocking circles. Okay. All right. So I'm going to go back now, and we're going to mark the points where A and B intersect. Normally we would do that on our DocuCam, but I'm going to at least show you, I'm sorry, not on our DocuCam, on Desmos, but again, I can't do that here, so we'll have to show it to you on the DocuCam. So I'm going to stop the share. I'm going to go back over and look at DocuCam. So here is circle A and B, and they want us to draw points where the two circles intersect. Well, they intersect, they cross each other here at this point up here and at this point down here. And so we call those C and D, okay? And so I can't put C and D here, but I can at least put the point in there when I go to Desmos. So I'm going to go ahead and do that. So I'm going to stop the share. I'm going to go over to Desmos, start the share, and I'm going to I'll click point over here, and I'll put a point here. That would be C, and that one would be D. Okay. All right. So let's go back to our DocuCam presentation. And so what we're going to do now, since both B and C are both on circle A, okay, so B and C are on circle A. B is the center, and I'm sorry, A is the center and B is right on the edge of it, then line segment AB here has to equal AC. Since A and C are both on circle B, since A and C are also on circle B, AB equals BC. So what they did was they drew lines between A and C and A and B and C, showing that those lengths are congruent. From A to C, that's just the radius of circle A. A to B is the radius of both circle A and circle B, which tells you that the two circles are congruent. And CB here is also the radius of, or BC rather, is the radius of B as well, because it goes from the center of B over here to its edge. So we're going to do the same thing. We're going to draw that little triangle there. So let's stop the share. And let's go back over to Desmos, and let's add the triangles. So I'm going to get the segment here. Now this one I've already got. This is A to B, all right? And then we go from here, so A to C, and then B to C, okay? So these are congruent. These sides are all equidistant. You can't see this because I can't show you a congruent symbol. I don't have means of doing that, okay? But at least I'm able to create this. Now, let's go back here and take a look at the next step in determining how to find a perpendicular bisector, because we're still mystified. How are we doing this? Well, we first come up with two congruent circles. Now we can come up with three congruent sides of a triangle that also happen to be the radius, the length of the radius of each of the circles. So what we add here, it kind of just continues on the thought. So let's go over here to the DocuCam. What we add on here, we say, hey, AB also equals, AB here also equals AD, which equals BD. It's the same thinking as we were creating up here. So you've got a kind of a mirror image set of triangles. So we'll go ahead, go back to Desmos and add that second triangle. So let's draw a line segment. And this one is going to go from A to D and from D to B. And now you see you've got two triangles that are congruent to one another. Okay. You also can see other geometric figures in it, but right now let's just think of them as two triangles. All right, so let's go back now. And what we're going to do is we're going to draw a line through C and D. So let's take a look at this. So looking at the bottom here, and what we're saying is, look, since you've got these two triangles, this is perpendicular bisector situation. D and C have got to be equidistant from A and B, right? So D and C, D is equidistant from A and B, C is equidistant from A and B, because all these measures are the same. So we're going to draw a line that goes from D to C with that thought in mind. So I'm going to go ahead and go back and show you Desmos. And we're going to draw a line that goes through C and D, right? Okay, so where does that take us? Let's go back and look at the DocuCam again. So the The set of points equidistant from A and B form the perpendicular bisector of A and B. Why do we know that? Because you see what we've done here by creating the interlocking circles and with a shared radius is we've created 90-degree angles here. And so that means A to B, the line segment AB is the perpendicular bisector of this line CD. Why do we know that? Well, we already have figured out that the distance from A to B, I'm sorry, A to the center here, where the 90-degree angle is equidistant as is the difference, as is the distances from that 90-degree angle, there's an unnamed point there, and B. So this has got to be a perpendicular bisector. Similarly, C, if we were to, again, go back and look at those triangle lines, we already know that the distance from A to C is the same as the distance from B to C, and we know the distance from A to D is the same distance as B to D. So this has got to be, this line, CD, has to help form the perpendicular bisector. It's at a 90-degree angle, as we've shown here. So you can read through this. So to complete the construction of the midpoint, we've got to put a midpoint between A and B. We have to carry out one last step. We have to mark the point where C, D, and AB intersect. So what we did was we put in a point B, okay? I'm sorry, point E right there in the middle. And since CD, this line, is the perpendicular bisector of AB, the intersection of E has to be the midpoint. And so that was what we were trying to prove at the beginning. What is the midpoint of a perpendicular bisector? Where do you find it? How do you find it? So we had to create a perpendicular bisector, which we just did here. This is a construction. So going back to our DocuCam, I'm sorry, not to our DocuCam, we're going to stop the share and go to Desmos. So going back to Desmos, we'll want to put a point in the middle. So I'm going to put that point right there. And now that point would be the point E that we were talking about, okay, in our presentation, okay. So I'll go back now. You can see how to do this. I'm giving you basically an embedded demonstration of Desmos, and you've got everything you need to be able to determine how to construct a perpendicular bisector and how to prove that you've got a perpendicular bisector and what the measures of different sides are related to the theorem. So going back, this is it. We're done with this, and I want you to have a wonderful day. We're going to go on next to working on angle measures. So I'll have a video 2.2 that I'll be doing for that. Okay, we're going to go ahead and stop. And again, have a really